All right, so on your handout here, want to just introduce some of the background information here. What we're going to use to figure out and try to understand the 3D models is something called valence shell electron pair repulsion. It's kind of a tongue twister, but it actually tells us exactly what it means. It's a model or a theory that helps us go from a 2D picture of a molecule in a Lewis structure to how it actually fills up space in 3 dimensions. So if we break it down, valence shell is just referring to outermost electrons, right? Valence shell means those that are involved in bonding, those that show up in a Lewis structure. And then electron pair repulsion means that anywhere we have an electron pair in our structure, those electron pairs are going to repel or be pushed apart because they're negatively charged. So anywhere we see a pair of electrons, whether it's in a bond or in a lone pair or non-bonding pair, well, we want to think of them as repelling and pushing each other apart. We've talked a little bit about this, but we haven't gotten into the details that we'll look at today. So one of the things we need to identify is what we call a region of electron density around a central atom. So that could be any of your 3 types of bonds, so a single bond, a double bond, or a triple bond, or it can be a lone pair, which is a non-bonding pair of electrons. Anytime we see one of these regions of electron density, in 3 dimensions, we want to push those regions apart as far as they can go because of that repulsion of the negative charges that make up the electron pairs. So what we want to be able to do by using this model is predict and visualize the 3D model. We want to predict the bond angles that are in the molecule, and we want to name the molecular shape. So we're going to work through several examples that we've seen before and build the 3D model using your pieces, okay? The straw pieces and the pipe cleaner pieces. So I'm going to go ahead on all of these and just give you the Lewis structure. These are ones that you've done before, either on a practice sheet or on a quiz. And you should know how to do it, but to save time, I'm just going to give them to you straight away. All right, so carbon dioxide. The Lewis structure for carbon dioxide has a central carbon. Central carbon. The 2 oxygen in CO2 have double bonds. And so we would have some non-bonding electrons on each oxygen. And again, you should be able to work this out on your own if you take a little time. But I'm going to go ahead and give it to you, and we'll work from there. And so I want to look at the central atom and identify some information, and that's going to help me figure out the 3D shape. So around the carbon, there are 2 regions of electron density, each bond. Okay, so this would be a place where we would find electrons because they're shared electrons. This would be a place where we would find shared electrons. And so we have 2 bonding regions and 0 lone pair regions. We do have lone pairs in the molecule, but none of them are on the central atom, so they don't impact the 3D shape. Okay. All right, so what we know about these regions here is that they are going to try to repel as far as they can from one another. And we want to show that with the models. So let me switch over to my camera. There we go. And so what we need to build CO2 is we need two of the straws. They are going to represent our bonds. And we need to connect them in the middle where the carbon is. Okay? So let me lay those aside. So we're going to take one of our pieces here, and we're just going to try to fold it in half as best we can. So try to kind of find the middle, and then you want to fold it kind of like that. So maybe you have kind of a V shape there. And I'm going to go ahead and kind of pinch it shut so that it kind of just looks like one solid piece. Okay. And that's going to be my connector between the two bonds. So I'm going to take the end that is kind of open, and I want to put the straw over both of those pieces so that it kind of holds that end together. And then I want to do the same on the other side. And that's how I'm going to represent this molecule. So we don't have them represented in their own part, but the carbon would be here in the middle. So you imagine a carbon kind of here, an oxygen here, and an oxygen here. Okay. Now, we could imagine, maybe there's some bend to the molecule, but the electron pair repulsion means that these bonds, the bonding regions, are going to try to get as far away from each other as possible. And the way they get as far away from each other as possible is if they're straight out in a linear shape. Okay? So the carbon dioxide molecule is actually linear, again, with the carbon in the middle and the oxygens out on either end. Jump back over here. All right. So how are we going to draw that? Well, let's go ahead and name the shape first of all. It is called a linear molecule. And I'm going to draw the carbon atom right in the middle. So I'm just going to put C with a circle around it to represent a carbon. And the two bonds are as far away from each other as possible. And so my oxygen atoms are going to be kind of out here on either end. And this is a case where the Lewis structure ends up looking a lot like the 3D structure, but that won't always be true. Okay, this is a bond, and I don't really worry about in this picture whether it is a double bond, a triple bond, or a single bond. So the other thing I want to note in this square is the bond angle. So what I mean by that is the angle here between the bonds. If it is linear, that means that the bond angle is 180 degrees. Okay. So we call it linear, we visualize it kind of like that, and the bond angle is 180 degrees. Okay. All right, any questions on that? That's the simplest of the ones we'll look at. All right, so moving on to the second page. Sulfur trioxide. Again, I'm going to give you the Lewis structure, but you would be expected to be able to do this on your own if asked. So sulfur, our central sulfur, has a double bond. To one of the oxygen. It has a single bond to the other two oxygen. And this oxygen would have two non-bonding pairs because it's a double bond. This one would have three non-bonding pairs. Same over here. And again, there really would be multiple structures. I could have put the double bond here or here. The real molecule is kind of a blend of those three. Okay. The sulfur in the middle has an octet because there's 2, 4, 6, 8 electrons involved in the bonds. Now, around the central atom, I would say there are now 3 regions of electron density, each of the 3 bonds. So 3 bonding regions and 0 lone pairs. The sulfur doesn't have any lone pairs on it. Okay. So let's use the models again to try to figure out the shape. Oops. All right, so we're going to take our model. We're going to go ahead and take it apart. I had my piece that I had kind of folded over. And now I need not just 2 attachment points, I need 3. So I'm going to kind of take the open end and just open it up a little bit into a V. And to make 3 attachment points, I'm going to take kind of halfway up and just bend a 90-degree angle in there on that side and the other side. Okay. So I've got my folded part, and then I've got a 90-degree bend. If I pinch it shut again, now you can see it's kind of T-shaped, and I can put a straw here, here, and here. So for sulfur trioxide, I want to have a bond to an oxygen, a bond to another oxygen, a bond to a third oxygen. So we get kind of a T shape at first. And that is kind of what the Lewis structure looked like, right? The Lewis structure kind of looked like a T shape. The actual molecule is not T-shaped. So what we need to do is, again, think about electron pair repulsion. Each of these bonds is negatively charged. We can get them further apart if we bend the shape into more of a Y shape, something like that. So we envision the sulfur in the middle, and then oxygen, oxygen, oxygen. Okay. And that is actually the shape of the molecule, something like that. So let me jump back over to the notes. The way I'm going to draw that is, well, actually, let's go ahead and name it first. The name is kind of a fancy name. It is named Trigonal Planar. So P-L-A-N-A-R. So trigonal planar. Trigonal because it has 3 parts. Planar, whoops, that's not what I wanted. There we go. Planar because there are 3 parts, but if you turn the molecule sideways, it's in a plane. It's flat, right? It's flat. It doesn't have depth to it. So the 3 pieces are in a plane. Trigonal because it has 3 parts. Okay. Now, how do I want to draw that? I'm going to go ahead and put the sulfur in the middle. And I need to show 3 bonding regions that are now not in a T shape, but in that kind of triangular shape. So let me first, I'll circle my sulfur atom. And I want to put an oxygen here, an oxygen here, and then the third oxygen kind of down here. So that's what a trigonal planar molecule will look like. And any molecule that has 3 bonding regions but 0 lone pair regions will take this shape. The other thing I want to know is the bond angle. So I want to know the angle between any of these pairs of bonds. So I'm looking at kind of a bond angle in here. And if I take 360 degrees and I divide it up evenly, that's going to be a 120-degree bond angle. And that should be 120 degrees in all 3 spots. So again, that's our goal on each of these. Can we represent the 3D structure? Can we know the bond angle, and can we name it? Okay. All right, moving on. Nitrite. Nitrite ion. So NO2 with an extra electron giving it a -1 charge. The Lewis structure will have a nitrogen as our central atom. It also has a double bond and a single bond. So I'll do one of the oxygens double bonded. And then a single bonded oxygen. And the nitrogen also has a non-bonding pair associated with it. The whole thing is carrying a negative charge. I should probably indicate that. Polyatomic ion. So if I focus on my central nitrogen, I still have 3 regions of electron density. I have a bond, a second bond, and then the non-bonding electrons are also a region of electron density. So it's total of 3, but now it's split between 2 bonds and 1 lone pair, so 1 non-bonding pair. Electrons here, here, and here. The 3D shape that we would make with the models, so sulfur trioxide, sulfur, 3 bonds. The only difference here is instead of having a 3rd bond, one of these is a non-bonding pair. So I'm just going to take that bond away, and this is actually the shape of the molecule. This part where you just see the pipe cleaner would be your non-bonding pair, your lone pair, and then you have an oxygen here and here, and a nitrogen in the middle. Okay. So let's represent that on the paper. And first, let's name it. This one does not have a fancy name. It is just called a bent molecule. I think chemists missed an opportunity there to come up with some fancy word that means bent, but they didn't. So I'm going to draw it with my nitrogen in the middle. And basically, I want to take this, I'm going to say remove this and this oxygen here. So I've got an oxygen, another oxygen. And then to show why it's bent, I often like to put the non-bonding pair in this diagram, because you can kind of see if that's negative, how it would push the bonds away and make it have a bent shape. Okay. Now, since I built it off the trigonal planar, I'm going to expect this bond angle to be similar to 120. But when you look at actual data, actual crystallography data, what tends to happen is the bond angle tends to be a little bit smaller. So it gets squeezed a little bit more, and it's usually somewhere in the neighborhood of about 115 degrees. Whereas this was about 120. So the thinking behind this is that the non-bonding pair has a little bit of a bigger repulsive effect and squeezes down that bond angle a little bit tighter than 120. If we think about our models, if this is the non-bonding pair, it pushes them so it's got a little bit more repulsion and takes it from 120 to maybe about 115. All right. All right, any questions on that one? All right, keep working. Methane, CH4. This one was on the last quiz. So methane, or carbon tetrahydride, if you prefer the systematic name, is a carbon with single bonds to 4 different hydrogen. So again, if I focus on my central atom, I actually have 4 regions of electron density here. They're all bonds, right? Electron pair, electron pair, electron pair, electron pair. 4 bonding regions, 0 lone pairs around the carbon. And the shape on this one's pretty interesting. So it's going to take a little bit of doing to build this from our models. So go ahead and disassemble our bent molecule. So I had my piece that was kind of made into a Y shape. I want to make it back into a T shape. So it has the bend in there. And I want to take my other pipe cleaner piece and make this same shape. So I'll review how we did that. We first want to just kind of find the center and fold it up upon itself like that. And then to make it into that T shape, once we have it bent, go about halfway down and just flex it out into a 90-degree angle or so, both ways. So we have T shape and T shape. Now, the way we want to put this together, we need 4 bonds. You take your 2 T shapes and you kind of just smush them together into a plus sign. And what I want to do is put one of my bonds here here, here, and here, okay? The tricky one is when you have the two different pieces, you just want to try to guide both wires into the straw, like this. Once that one's done, the rest is kind of easy. The other tricky one is, again, the one that has two different wires, but you want both wires to go into the straw. There we go. And then here, and then here. So we have kind of a plus shape for CH4. Now that looks a lot like the Lewis structure. There's a carbon in the middle, hydrogen, 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 hydrogen. 90-degree separation here. The problem is this is not the furthest apart we can get the bonds. Right now, several of them are 90, but this would be 180 degrees from here to here, right? So here's the trick. You want to take your plus shape, and you want to take two ends and kind of bend them a little bit, something like that. Kind of a seesaw shape. And then I want to take the other two, and I want to bend them up and away from that. So I had my two here, and then I took the other two and bent it like that. Okay. I'll show the class kind of here. So you end up with something like this. What you have is kind of a pyramid at the bottom, if you've done them all equally. Kind of hard to see with my camera. See if I can get it here. So you kind of have to play around with it to get them all equal. Not sure I'm there yet. But I have, in a sense, if I set it down, a pyramid shape. And then this one on the top is kind of coming off the top of the pyramid. Let me see if I can get a good side view of it. So a pyramid at the bottom, kind of here. And then one rising from the top. It's kind of a flat, squat pyramid in that orientation. And if I've done it correctly, I can rotate it. And I can always kind of come back to that squat pyramid shape with one coming off the top. So it takes a little bit of playing to get them all equal. You might have to flex it around. Okay. Something like that. Okay, so how are we going to draw that, and what are we going to call it? So here's how I draw it. It's a little bit tricky because we need to show 3 dimensions because now we have depth to the molecule. So I'm going to go ahead and put my carbon in the middle. And I'm going to try to make the pyramid kind of down here, and then one hydrogen comes straight off the top. So I'm going to go ahead and put that hydrogen in first. Okay. And then, so I'm trying to make kind of a squat pyramid at the bottom. I'm going to make a hydrogen coming out here. And then the thing with the shape is the hydrogen that's going to bond here is actually kind of, it should be in front of the screen a little bit, right? It's coming towards you. And there's no great way to show that, but one way you'll see it sometimes drawn is with like kind of a wedge shape. So kind of a wedge that gets thicker as it moves forward. I'm going to do my best. You do the same. It's not going to be perfect. So this hydrogen, because of that kind of wedge shape, is supposed to be kind of in front of the screen. And then the fourth hydrogen is kind of sitting behind it over here. So we can do kind of a reverse wedge there and kind of make it get thinner. And what we're trying to do is show some depth. So we've got kind of this squat, flat pyramid, one up top. Each of these is an H, okay? And if you work out the geometry and you just got it perfect so that they're all equally spaced and far apart as possible, and if you could measure the angle here, and this would be the measure of the angle anywhere between your hydrogens and carbon, it actually comes out to be 109.5 degrees. And each of these would be 109.5.
Are we going to have to memorize the degrees?
No, I don't think I'll have a quiz on the degree angles, but we're going to do a little mini project, and you could use this as a reference. Now, as far as a name, we didn't name it yet. It's called tetrahedral. So tetra for four, kind of four parts, right? Tetra, H-E-D-R-A-L. Let me see if I can move that. Tetrahedral is this shape. Okay. That's the hardest one to build in 3 dimensions. Okay, continuing on, we just have 2 more to do. We can get through these, I think. We have ammonia, Lewis structure. Is often drawn like this, a central nitrogen. It has 3 hydrogen single bonds. And it does have a lone pair, a non-bonding pair on the nitrogen. So its similarity to methane is that it has 4 regions of electron density, 3 bonds, and 1 lone pair, 1 non-bonding pair. Okay. So to think about this structure, go back to my model. Got my kind of flat pyramid here. I could choose any one of these, and it's no longer a bond, it's a lone electron. So I'm just going to pluck the one off the top here. And if you're lucky, it's one of the ones that had a fold in it. Kind of stays together better if that's the case. So now what I have is just the kind of squat pyramid left. This would be the 2 non-bonding electrons. The nitrogen here would be at kind of the peak here of the pyramid, and the hydrogens would be out on the sides. Okay, so looking at it it looks a lot like the Trigonal Planar, but there's depth to it now. Okay, so the name actually, I'm going to start with the name this time, is still trigonal. So trigonal for the kind of 3 parts of the shape. This one was trigonal planar because it was all in one flat plane. This one is called, I'm going to spell it first, so it's the word pyramid. And then it has AL. So this was planar, this was tetrahedral. It's actually pronounced pyramidal, which is a tongue twister. But if you want to think of it as pyramidal, that's really what it means, right? We take this tetrahedral shape, we take one of the pieces off, and we're left with that pyramid shape. So here, I might draw it, my nitrogen, kind of at the top of the pyramid. I'm going to draw the same shape I have down here for my 3 hydrogen. So this hydrogen, I've got my hydrogen that kind of comes forward with the wedge shape. My hydrogen that goes backwards with kind of the reverse wedge shape. And so trying to show that this has some depth to it. And then I like to put the non-bonding pair on top, and that explains why we're not just trigonal planar. That non-bonding pair squeezes the hydrogen bonds here, or the bonds with the hydrogen downward. And if it were based on the tetrahedral shape, we would expect these bond angles to be 109.5. Again, from the crystallography data, we know that that bond actually gets compressed a little bit tighter by the non-bonding electron. So this angle ends up, for most molecules, being closer to 107 degrees. So it would be about 109.5 with tetrahedral. If we squeeze it down a little bit more, it's closer to 107. And that's just a ballpark figure. different molecules will have different bond angles based on also having different elements involved. All right, one more to go. Good old water. Water is often drawn like this. 2 hydrogen linked up with the oxygen with single bonds. There are 2 non-bonding pairs on the oxygen. So if I look around the oxygen, I still have 4 regions of electron density. 2 of them are bonds, here and here, and 2 are non-bonds, right? Lone pairs, non-bonding electron pairs. And just like I took tetrahedral and plucked off one of the hydrogen, I'm going to do the same thing for water. So one of these 3 hydrogen is going to be no longer a bond, it's a non-bonding pair. All right, so let me go back to the model. I had my pyramid, right? I'm just going to pick one and remove it. And it kind of works best if the other one that you remove has the fold in it, so I'm going to try to find that one. Of course, it's the last one. It just stays together a little bit better if we do that. So there's my other fold. So now I have, again, a bent shape, 2 non-bonding pairs that are kind of squeezing it down, and the water molecule is in fact bent, okay? Something like this. In drawing it for our notes, I'm going to put the oxygen here at kind of the peak of the bend. There's a hydrogen here, hydrogen here, all right, I'll circle that. It's an oxygen atom. And the oxygen atom has 2 non-bonding electrons, and we think of those as kind of squeezing the bonds into that bent shape. This one is also just called bent. Okay. Now the bond angle is squeezed down even a little bit further from 107 degrees on this type of molecule. And for water, it ends up being about 104.5 degrees. And that's a ballpark figure for other similar bent molecules with 2 non-bonding pairs and 2 bonds. Okay. For water in particular, the fact that it's bent actually has a huge impact on the properties of water. So if you know anything about snowflakes being 6-sided, that's actually due to the bent shape. So if I put these together and I were to build together, they would kind of form a hexagon shape pretty closely, hexagon having 6 sides. So the crystal structure of water, like you would see in a snowflake, is a direct result of the molecule actually being bent. If it were linear or some other shape, you would expect the crystals to form kind of in a different way. All right. All right, so I'll go ahead and stop the video. You guys can put those in your Ziploc bags. For anyone who is absent on this day, I'm happy to give you the model pieces if you would like to make your own model. We would just need to figure out how to get those in your hands. Sometimes having the 3D shape in front of you is useful to have. So